going to see software from measurement point of view. What actually is what actually we mean by measuring software, because in software we don't have any dimensions, and measuring something which don't have a dimension is something different from what we have seen in our basic maths or something else. So we need to see how this measurement actually can help, and how we can do this measurement in context of software, and how actually we can use this data to assess the software. This is also very important. So once you do some measurement, you're going to get certain data, and how actually you can use that data for analysis, maybe in maintenance or in a different phase of the software. So first, let's see what actually this measurement means. So if I talk about measurement as a simple definition from any book, so it is about a process by which actually you assign some numbers to some attributes or features of an entity. For example, if I am an entity, you can assign my body temperature a particular number, which can be, let's assume, 36.8 degrees Celsius. So this number is actually the measurement which represents an attribute, means the body temperature. So measurement is like is something by which actually you assign some numbers, by actually you want to get some information, and we are going to see how actually we can get this information, and how actually we perform measurement in terms of software engineering. So first, let's see what actually why actually we want to use measurement. So once we are using measurement, it will give you some understanding based on which you can see, or you can the current activity where actually you're performing some task can be visible, and you can establish certain guidelines. For example, if I take an example of software testing, if you have a tool which actually can report how many bugs have been identified in a whole day, then actually you can understand with the help of this tool. First, you are measuring how many bugs you are getting in a day, and based on which you can clearly see like with this data, the value which you have received. For example, if there is 10 bugs a day, then we can actually understand from this what is the rate of bugs we are getting from a piece of component or from a particular module, based on which you can also set certain guidelines. For example, if a particular component is giving you let's say too much of bugs, let's say the out of 10, if a particular if there are 3 components, and in these 3 components, if 2 components are giving you the majority of these bugs, then maybe you can set certain guidelines for the tester that they need to cover approximate 80 or 70% of this code to see the bugs. So you can see, like, with the help of measurement, you can understand what is going on in the software. Like in our example, you can see what is going on in this testing, and then based on which you can also assign certain guidelines, with the help of which you can improve the whole process. Measurement also allows us to control. It actually can predict outcomes, and you can change the process. For example, in the whole software development life cycle, from requirement gathering to maintenance, you can actually control the process. How you can control, like, for example, you can set certain time period for a particular phase, and if you are lacking behind that particular phase, then actually you can actually control, or you can change the process, or you can perform certain modification in that phase, so that in the next phase you can be aligned with the time frame. So actually it can help you to control the whole process as a whole, and it also encourages us to improve. For example, if you are measuring the performance or the quality of a software, and you found out, like in the last class we saw this quality model has 8 different characteristics, and you found out that like the security parameter is something which your software is not fulfilling, and then based on which actually you can always improve your software. So overall, if you see, measurement is very important in the whole software maintenance as well as in different life cycle of software development, which is going to help you to understand, control, and improve. These are actually the 3 bullet points that is the main use of measurement. Now, there are some propositions with which you may agree and with which you may not agree. For example, I can start with the last one, which tells you if you add more people to a project, it will be completed faster. So this is something with which you can agree and disagree. Let's assume if we have a team of 5 people, and somehow if we increase the number of people from 5 to 10, and the task which we are thinking to complete in a month, now maybe we can complete the same task in 20 days. It is possible. But if we think like by putting number of people can actually make the process fast, then the one can actually put 300 people in a team, and he can assume the next day we can complete the task. So it's not like you can put as number of people and you can make the process fast. So putting 300 people in a team and expecting like the project is going to complete the next day, it's something which is beyond our imagination, or it is not something which actually can happen. Similarly, if you see the next line, which talks about the more you test the system, the more reliable it will be in the field. However, yeah, with this also you may agree and you may not. For example, if you are testing a particular system, yes, by testing you can say the system is bug free, and you can actually claim that like the system is reliable and it can be efficient at the same time. But however, let's assume if you are using the same test suits, test cases that have been used or that were designed 2 or 3 years back, and you have not done any changes in those test cases, and you are using the same test case for the new software in which you have done some modification and some addition. So the problem here will be the test case will pass, but the thing is these test cases are somehow they are obsolete, and they are not actually designed for the current software that you have. So again, like I told you, you can actually prove or you can actually disprove these statements based on your own understanding. And similarly, there is one more things like the developers who actually drink coffee in the morning produce better code than those who do drink orange juice. So this is also something which you can see. People who actually come to work, they normally take coffee and they start doing their work. It's not like people are taking orange juice and they start working. Or you may not see people after if they are working in an organization after 1 or 2 hours, you often see they use a term called coffee break. You will never see a juice break or orange juice break. So again, like this is something with actually you can see how actually these actually impacts the whole part of the measurement. Yeah, so in the last class, I talked about this ISO IEC 25010 model. And if you remember this model actually talks about how you can measure a target computer system. So we talked about 3 different models, and we saw 2 models in detail. One was the product quality model, which had 8 characteristics, and those 8 characteristics was like security, usability, portability, and so on. And similarly, we had we saw some characteristics for quality in use model, based on which we were trying to measure how actually the product, once it is delivered, how actually we can measure its effectiveness, its reliability, and so on. So there were, I think, 4 or 5 different characteristics based on which we can measure the quality in use of a particular product. And then in the center, if you see of this diagram, we have a data quality model, which actually talks about this data quality model actually talks about how the data is actually going to impact the overall performance. So this whole framework, or this whole model, if you see, is designed to measure something. For example, the product quality model, the main black arrows which are not dotted, if you see those arrows, so those things are something which are directly measured by these models. For example, the product quality model is directly measuring the target software within the target computer system. Similarly, we have a data quality model, which actually measures the target data, how the data is being analyzed, how the data has been collected, and so on. And last, we have quality in use model, which actually takes everything in the context, because it's not only about the system, it is about different factors actually, which is going to make the software working quality to be high. For example, how actually it is interacting with the users, in which actually environment you are executing the whole software, what are the different stakeholders, and many other things. So it relies on multiple different factors to calculate the overall measurement. So ISO 25010 measurement is something which we always used to measure a target software, and based on these three different quality models. But in software measurement, if I talk when we talk about software and its process, it's not only about the product, it's about two more things: process and people. So this is why this is called 3 Ps of software measurement, in which we not only consider product, but we also see the process and people. So product is the actual software that actually is being designed for which is going to be used by the end user. And second, we have this process. This process actually means what steps or what methods you have used to design the whole software. And the third one is the people who actually were the responsible for designing or doing this maintenance, or doing this operation things for the whole software. So if you see in the whole this process, means in the whole life cycle, we have product, process, and people, and we need to measure these three things together. It's not only about product, it's also about process and people. And we are going to see in our next slides why actually we want product, process, and people, and how actually we can measure them. So let's start first with measuring the product. So product actually refers to the actual software system, documentation, and other deliverables. So it is actually a collection of software that you have designed, some documentation, and of course some deliverables. For example, in a software development lifecycle, you get multiple different deliverables. You have different, like you have a requirement specification, you have some test suits, test cases, you have some design, some design things. You have some blueprints for design. Then you have some maintenance code. You have some other deliverables, like for example, testing. Like if you perform test, then you get a report, like how actually the software was working in the whole cycle, and so on. So there are multiple things that actually is the product is made up of. And then we want to analyze this product, and we want to measure this product in different aspects. And what this aspects is, we can actually measure this product based on size. And the size actually can be in multiple dimensions. Like, for example, the size can be how many lines of codes are there in the whole software, because ultimately lines of code is going to tell you what actually is the complexity of the whole software. And then you can also one can be line of code, and second can be like what kind of functionality the whole software provides you, whether it is giving you the desired functionality that was asked by the customers, and how much how much actually cost has been put on the whole product, starting from the development to deployment as well as in operation phase. And then we have different quality attributes which actually we can measure in terms of a product. We have seen these quality attributes, and we are specifically talking about that 25010 model, quality model, in which we have those 8 different attributes or characteristics based on which actually we can measure the product. So if you see the whole analysis of a product, it's not only about the quality, it's about the cost, it's about the functionality actually which it is going to offer, and overall size, and in different aspects of size we can have. And similarly, if I talk about process, we can measure process. We want to measure actually process because this is something which includes different methods, steps, which are involved in developing the whole product. So this is why it is very important. Like we need to measure the whole process, and this actually includes various different aspects. First can be like what life cycle we have used. There are multiple life cycles that we are familiar with. For example, waterfall, agile, extreme programming, and so on. So it depends like which life cycle you have used, because every life cycle is going to have a certain aspects. For example, in waterfall model, like after every phase you get as an output a very heavy documentation, and the product is delivered once the whole life cycle is completed. But it's not the same with extreme programming, where actually you just take the requirement and you build and you just give the product to the user, and in next iteration again you do some changes and so on. So it actually so this analysis or the measuring of the process is going to depend on the life cycle that you are going to use, and the deliverables, like what deliverables are produced. For example, in a waterfall model, the main deliverable that you can get from the first requirement in phase is like you can get some you can get requirement specification from the user, and from which actually you can design the whole software. Means you can get a blueprint, and based on which then you can perform you can write the whole code. So you can get a deliverable set of code and documentation, and then testing and so on. So you can see you are going to get different deliverables with the process actually which you are going to use. And ultimately we also want to know how actually these deliverables are going to be analyzed, how we are going to analyze these things. Maybe we can have some check and inspection to evaluate what actually is going on through the whole process. And we also want to know like how can the process help to produce product faster. So this is also one question that by measuring the process you can get the answer. Like for example, if you are investing more time, again, like if you're investing more time in a particular process, for example in testing, then you can always come back, you can take feedback, and you can come back to the same phase, and you can see how actually and what we can do to make the whole process fast, so that ultimately the product can be delivered at faster rate. And yes, and how can the process help to produce better products? This question also can be answered if you are measuring the process, because you can get the feedback from your management, as well as you can get feedback from once the product is delivered. You can also get feedback from the user, and from the management as point of view, like they can give you the feedback where actually you are going wrong, and which process actually is delaying the overall production of the software. So this is why actually the measuring the process is very important, because it is going to give you an analysis how actually you are going from starting phase to the end phase of the whole product building. Third is measuring the people. Here, people actually means the people who are actually going to be involved in the developing phase. So why actually we want to measure the people? Because it turns out that people have a huge impact on the whole product. For example, you may want to know how fast a person or a developer is actually working, because you want to hire people who actually work faster, who have some domain knowledge. and of a particular language, or maybe of a particular technology. Because if someone has a domain knowledge of a particular technology or of an area, they can actually work very fast compared to one who don't have. So by this, you want to measure people like based on how fast they work. In testing, you may go and you can check how much bugs do they produce. Maybe they are writing huge codes, but ultimately those codes are producing lots of bugs. So you want to analyze the people on basis of bugs actually which they are producing. And of course you can also check how many sick leaves do they take, because this also is going to impact the overall product. So the person who is taking more sick leave, it means it may happen like the overall productivity can go down. And so the management is also more concerned about how many sick leaves a particular person or a developer or a person who is somehow is there in the development team is taking. And it is very controversial, like people actually do not want to be being turned into numbers. So when you are treating people in the whole team as a sample, no one actually wants to become the part of that samples to be evaluated. So this is also something which is a problematic task to measure actually the people who are there, but somehow it needs to be done. And if you see the overall measurement, what we are seeing, the product, the process, and the people, each measurement actually can only be done once you have data. So the data is very important for performing measurement. If you don't have data, so you cannot perform measurement for a product, or a process, or for a people. Like in the first example I told you, a body temperature, if your body temperature is 36 point something Celsius, so you need this value actually to do some analysis, whether you have a fever or whether you don't have a fever. So similarly, in software engineering context, you need to have certain data to perform measurement in terms of product, process, and people. So collecting the data is very important, and it is also a very challenging task because when you do this data collection thing, it should follow some systematic approach, and you need to ensure, like by the end, that the data that you have received or you have collected, it should give you some meaningful information. And this is actually needs to be done without being a burden on the development team. For example, you may try to be more unintrusive as possible. For example, this actually means you should not put more burden, or the whole data collection process should be designed in such a way that it should be integrated with the normal flow of the team. So there should not be some extra task given or should be allotted to the people who are there in the development process, because ultimately if you do this, the whole process means it is going to delay the production of the software. You can make the whole data collection part automatic. You can design certain tools, you can write some programs, or maybe you can use some tools which are there available, and the whole data collection can be done without any human intervention. And also, let me tell you, this whole data collection part is going to be very expensive. So you need to convince your management, and convincing management sometimes turns out to be very difficult, because management wants, like, if you are doing this data collection, what in return the company is going to get. So convincing someone, especially the management people, in terms of money is very difficult, and it's very challenging task. And because the whole collection process is going to be expensive in the sense, there will be certain delays, and people have to invest little bit of extra time in this data collection process in order to fill the whole process. However, you can follow this systematic approach in the data collection, which which includes, for example, you need to first establish the goal of data collection, why actually you want to collect the data. For example, you may be interested in collecting data of software testing, how many bugs means the whole team is identifying in a particular software, or the goal can be of the customer feedback. Once the product is released, how actually the customer is using the software, how easy it is, how user friendly it is, how many bugs are being identified. So you need to set a certain goal of data collection, and based on which you need to develop list of questions of interest, which actually is going to answer or which is going to question that particular goal. For example, how many bugs have been identified per day, in how many modules, let's say if there is 30 or 40 modules, how many modules you are getting bugs, and so on. So you need to develop certain questions that you need to ask, and then you can establish data categories, maybe some class. One class can be for bugs, like for software testing, other can be for customer feedback, and so on. And once you have separated the data into different categories, then maybe you can also then the next step that you can follow is you can design, and you can design data collection forms and programs. Maybe you can write certain programs or forms in which user actually can fill the data, or you can design an automatic form with the help of which you don't have to fill data manually, and you can just use it for the data collection. But ultimately, you need to test these forms and programs, whether actually these forms and programs is actually working or not. And then once you know, like, your form, the tool that you have designed for data collection actually is working, then you can finally deploy, and you can collect the data from different aspects. From means you can check the goal from which aspect you want to collect the data, and you can actually collect, and you can validate the data. Validation actually means the data should be consistent. It should actually cover all information that you are looking for. And once you have the data that you are looking for, you can perform analysis on data. Maybe you can use some AI techniques, or you can use some statistical approach to get the hidden patterns, or to know more about the data, like what actually the trends are inside the data, and so on. So the collecting software engineering data is very important, and because ultimately the measurement heavily depends on the data that you are going to collect. And this is a systematic approach which actually you can follow to collect the data in software engineering in any actually field. So in this slide, actually, I'm trying to show you some examples of what we have seen in measurement terms. So the first slide actually talks about, so this is a metric from which has been taken from Motorola. And if you see, this is a very big multinational company which has so many products, not only mobile phone, they have their own software and many other things. So the goals, just look at the goals, what they have. They have 7 goals, which talks about improve project planning, increase defect containment, increase software reliability, defect density, customer service, cost of non-conformance, software productivity. So overall, the whole goal, if you see, is related to the product. So they are more emphasized towards building the product such that it should be bug-free. It should how actually you can improve the overall customer service and software productivity, how it can be done, and so on. So the whole what I can see from this slide is the whole Motorola is more focused towards the product itself, and they have different measurement areas. For example, deliver defects, process effectiveness, software reliability, adherence to schedule, time that problems remain open, and so on. And next, we have IBM. And if you see this IBM, they are the main goal of IBM, if you see, is customer satisfaction, post-release defect rates, customer problem calls, fix response time, number of defective fixes. So in this thing, IBM actually is more looking towards the I think towards the process, like that means once the product is being released, they want to know the maintenance process. Actually, the whole maintenance process is being seen in this example. Similarly, if I talk about Hewlett Packard, they are more concerned about like how the defects are fixed per day, what is the average engineering hours, and how many people are fixing these defects, and defects per testing time, and so on. So if you see it, they are more inclined towards the people and how actually these defects are actually being done. So we have three different companies, and all three different companies have different approach for different measurement criteria, which actually gives us an example how different metrics can be actually formulated for different companies. So let's see what different types of measurement actually we have. So we have three different notion in measurement. The first one is measure, the second is metric, and third is indicator. So measure, if you can see the definition, what is there. It is an appraisal or ascertainment by comparing to a standard. An example is like Joe's body temperature is 37.5 degrees Celsius. So you can see like this Joe's body temperature can be one of the feature, and the reading that you have 37.5 degree can be a measure that you actually have obtained. And if I talk about the metric that is being used here is degree Celsius, actually, which tells you like what is the body temperature of Joe. And this actually also gives you an indication, like this value also gives you an indication, like his body temperature is going towards fever, because the range, once he crosses 37.5 and if he enters 37.6, this indicates that his body has now fever. So these three metrics, or these three notions, measure, metric, and indicator, is going to be used very frequently in order to perform the measurement of a software. And then in measurements, we also have two more notions. The first one is reliability, which actually tells you the consistency of a number of measurements that have been done using the same measurement method. And then we have the notion of concept, which actually tells you whether the measurement or metric that you have done really actually gives you what you want. So we can see these two things, reliability and validity, with this example. For example, if you see the first case, in the first case, the main target of this diagram is to show you like we want some data points which should be close to the central black spot. However, we have done measurement and we found like the data points are not close to the dark center point, but however they all are very close to each other. So what we can say is they are reliable because all data points are giving you a measurement which are something common, means you are doing this measurement again and again, and you're getting some data points which are very close to each other. So it means they are reliable because they are not changing drastically. However, they are not valid because our ultimate goal was to have those data points to close, means we were looking for the data points that should be close to the black center point. In the second diagram, if you see, we have again, we have collected the data, and the data points are somehow scattered around the black spot. Now, if you see this diagram, you can say these are not reliable because the data points, every time you measure, you're getting a different data points at different place. So they are not close to each other. So they are not reliable, but they are valid in the sense they are very close to the dark spot in the center. So we can say with this diagram, like this is valid, but they are not reliable. However, if you see the third diagram, in this third diagram, all data points are very close to the dark spot, and they are also close to each other. So in this case, we can say the measurement that we have done, they are not only reliable, but they are also valid, because we were trying to measure these points, actually something related to this black spot. So this is how reliability and validity notion actually means in terms of measurement. Then we also have measuring stuff known on measuring stuff. We also have an ISO IEC 29119, which actually is being used during software testing. So during software testing, we use this model, and large project or organization actually need this measurement planning, and they follow this ISO IEC 29119. And there are certain list of questions actually when you follow this when you follow this model, it gives you the answers. For example, why are things measured? Why actually you are measuring things? What is measured? Maybe you want to measure some quality of the product, or maybe you want to measure different aspects of the product. And who will measure? You want to know, like, who actually is going to measure this. Maybe a software tester is going to measure, or actually the management team is going to measure the whole process. So these answers actually it means you are going to get once you follow this model. What parts of the system are going to be measured? It can be like you want to measure a single component, or some components which actually are related to each other, or it may happen you want to measure the whole software as a whole. When you want to measure from the starting of the process, or you want to measure once the product has been done and it is ready to be combined with other modules. And how will the data be collected and analyzed? We saw this, like how actually we can follow a systematic approach for collecting and analyzing the data. So if you follow this ISO IEC 29119, you can get answers for these questions, which actually can be used by different large organization, which needs actually this measurement planning before they start building the product. And this is something very general terms, requirements for any measurement, whatever you are designing, or whatever things are happening within the software development lifecycle. These are the four basic requirements that the whole software development thing needs to follow, or it should give you. The first one is the measurement is not dependent on the people or environment or the measurement process. This is something is something that needs to be understood. And the second thing is the product that you are going to develop, it should be accurate, and it should be repeatable, because once you do the repetition, you can get the consistency, and you can understand the reliability of the whole software, and ultimately it is going to give you the overall usability and robustness of the whole software. And then it also from economics times, like the measurement provides information which is useful, and ultimately it is going to save more than the measurement cost. Reusability, this factor actually means the measurement should be repeatable again, and repeated measurements provide metrics that we saw in our previous slides. When you perform repetition, you get reliable, and some metrics you find by the help of which ultimately you can compare to the previous measurement, and you can get what actually is going on in the whole process, and based on which the whole you can get a feedback loop. You can generate a feedback loop with the help of which you can actually improve the overall quality of the software. And there are different types of measurements for process. So the first one that we saw is it is actually based on ISO IEC 29119 testing process. and we just saw this process, and actually what things this process is going to answer. And once you follow this measurement, what actually things it is going to cover, it is mentioned in this slide. Like for example, this ISO 29119 testing process measurement is used for raw as well as for generated data, like what was the input and what was the input you are going to give to the whole process. Work plan based indicators, project status based indicators. So there are multiple indicators actually with which you can actually measure what actually is the performance or the quality of the whole testing process. And similarly for the product, we have ISO IEC 25010, which actually measures the whole product on the basis of these 8 characteristics. And we have seen these 8 characteristics in our second in our quality class. So you can also check. Maybe you can go back to that slide and you can just check what actually this functionality means: compatibility, reliability, security. What are these different factors, and how actually these factors are going to impact the overall software quality. Now, yes, so we have now little information about what is measurement and why and what we can actually measure. We can actually measure process, people, and product, and there are different aspects actually by which you can actually perform this measurement. There are some mathematical models that actually can be used to perform measurement, and one of them is function point. So instead of measuring size, means size in the sense the line of codes or the overall complexity of the software, function points actually we can use to measure the overall functionality that the whole software is going to offer. And this function point was invented by Albrecht at IBM in 1979, and it is being used in most of the companies with little modification. So we will see what actually this function point is and how actually we can calculate a function point. So first, the general definition of function point is like we use this metrics for measuring the various functions of a software application, and function point metrics actually measures functionality from user point of view, like on the basis of what users have asked for from the software and what actually they are getting out from the software. And the main objective of function point analysis is to measure software by actually quantifying the functionality that the software provides to the user primarily based on the logical design. We are going to see with an example how these things actually works. And the main objective of function point analysis is first to measure functionality that actually user has requested, and they are actually getting once the product is being built. And second is it can also measure software development and maintenance independently of whatever technology or you have used for implementing the product. And what are the benefits of function point analysis? Like organization do apply this function point analysis because it is a tool which actually determines the size of a purchase application by just counting overall the functions actually that the whole package is going to provide. It is also going to help users to determine the benefit of an application package to their organization by just counting the total functions, which actually that actually can specifically match their requirement. It is also a tool actually to measure the units of a software product to support quality and predictive analysis, and it is a vehicle to estimate the cost and resources required for the whole software development and maintenance. And let's see how actually these things are being done mathematically. So the simplest way to so in function point we have 5 different parameters. First one is the number of external input. The second is number of external output. Third is number of logical internal file. and fourth is number of external interface file. Fifth is number of external inquiries. And these parameters, if you see, they are multiplied by certain numbers, which actually is coming from this table, which is same or which is common for every software that actually uses function point. So the number which you saw here, which actually we are multiplying. Okay, so these parameters, I will discuss what these parameters are with an example. But let's first go to these numbers, which actually we are multiplying this with these parameters. So these are different measurement parameters, and for these parameters, we have certain numbers. And these numbers are actually called as weighting factors. So these weighting factors have been divided into three different parts: simple, average, and complex. For most of the software that we actually for which we calculate this function point, we are more interested in average rather than simple and complex. And you need to understand, like in any problem, or if you have any questions, if they have not mentioned like which weighting factor they are going to use, like is it simple, average, or complex, then in that case you need to go with average. If it is not mentioned, if they have explicitly mentioned like they are interested in simple or complex, then you can actually multiply these weighting factors with these measurement parameters. So now let's take an example and then try to understand this example. So in this example, we are given the query is, we need to develop a system which allows customer to report bugs. So a system which actually can report bugs. So this is external input which your system is going to take in a product. These reports will be stored in a file. So you are storing this in a file, which is going to be is an a logical internal file, with the help of which your system is going to perform certain calculation. And developers will receive a daily report. So your system is going to generate certain output. The first output is receive a daily report with new bugs, which they need to solve. So one external output is they are going to receive a daily report for bugs for the product that they have developed. Customer will also receive a daily status report for bugs which they have submitted. So input is the report bugs that the customers are submitting to the product, and they are getting two output from this software. One is for the developer, which actually tells you the daily report, and the other is the daily status report for bugs, which actually is for the customer. So if you see in this, we have one input and we have two outputs so far, and we have one logical internal file like that the system is going to use, which in our case it is reports that are going to be stored in a file. And then we have management can query the system for a summary information of a particular months. So this is external query that is going to come for your system. So in this example, we have one external queries. So you need to count first. You need to count how if I go back to this table. So in this table, if you see, the second column is count. So in the count, you need to mention how many number of external input you have calculated. Means there is in the query, how many external output is in the query, how many number of external inquiries are there in the query, number of external file, number of external of external interface. If someone is not there, you can just put it put 0. And then the next okay, so this is how it is. So you have placed those numbers here, and we don't have any external interface file, so for that we have 0. So that's how we can calculate the total functionality, because we have not mentioned it is simple or complex. So in this case, we can assume, and we should assume, and we should take the average parameter value for each of these parameters. So similarly, we have multiplied it by 4, 5, 10, 7, 4, and we got the total functionality is 28. So with this 28 number, you can actually assume this thing is, if the total function point is very high, it means the customer is going to get more functionality from the software. And the complexity is also is also a little complex, because more functionality is going to come once the software has those different kinds of feature. And if you have less function point number, it means the overall functionality you are going to get from the software is less. However, this function point actually was extended, and because these function points were not sufficient, were insufficient actually for the systems which have multiple different features. For example, they distributed functionality, means distributed processing. These features are something which actually function point doesn't calculate. And because of this, there have been different extension to the function point, and these are some examples. For example, one of the example is general system characteristics, GSC extension. Second is 3D function point, object point, feature point, scope management, and COCOMO model. So there are different models that actually you can go through by your own, and you can just check how function point is the base, and how you are using this base to calculate different aspects, and how actually these aspects are related in software maintenance. However, in this slide, we are going to see the first one, GSC extension. So why actually we want this GSC extension is because the original function point actually do not address certain functionality of a overall system, like I told you. For example, distributed functionality or the performance of optimization, etc. So this GSC actually involves certain more parameters apart from those that you have seen in the previous slides. So there are 14 more questions about the system that is being asked in GSC. And then the original function point is modified based on these 14 questions. And what are these 14 questions? These are data communication, distributed functions, performance, heavily used configuration, transaction rate. So these are self-explanatory how in a system context, what actually these things means. End user efficiency, online update, complex processing, reusability, installation ease, operational ease, multiple sites, facilitation of chance. So these are 14 characteristics that have been used as an extension in function point. And how actually this thing works. So for each 14 parameters, we assign certain values. The analyst or software engineer assigns certain values, and these values actually ranges from 0 to 5, where 0 actually means not applicable and 5 is essential. And then we have a notion called value adjustment factor, which we actually calculate, and the formula is 0.65 plus 0.01 summation of CI. CI over here represents actually those 14 factors that you are going to add. So once you get this value adjustment factor, you just multiply with the function point that you have calculated, and then you get the new function point for the GSC function point for the whole system. So for example, in this, we can take an example. Let's take a bug reporting system in which the analyst, let's assume he gives certain numbers to these multiple characteristics, and these numbers are like for data communication it is 5, for distributed function is 0, and how these numbers actually we are assigning. So this is not this is out of scope for right now for this context. So we are not interested how these numbers have been generated. So because we are not what our task is how to calculate GSC. So once we have those things, we can actually, once we have these numbers, we can calculate, but how to come up with these numbers that we are not going to see in these slides. So once you have these numbers for each parameters, you can simply add them together, and you can get what is the total sum. So you get a total score of 25. And if you remember the previous formula that we had for value adjustment factor, which is 0.65 plus 0.01. And now you have this summation of CI for this whole 14 characteristics, which is we have calculated it is 25. So you get a value adjustment factor of 0.9. And now you can calculate the new function point, which is function point multiplied by this value adjustment point 0.9. And we, in the previous example, we calculated, like we had this FP of 48, and now the function count is 25.2. So this GSC extension can increase or decrease the original count, but this is more useful when you have a very big, large system, in which actually function point cannot calculate the overall functionality. So I have just showed you how actually you can do this calculation, and why actually we need this GSC. But you can also go through by your own, and you can just check why and what and when actually we have to use GSC in software maintenance by your own. Function point we saw, we also saw GSC, and then again we have one more metric called cyclomatic complexity matrix, which is actually based on a graph theory. And we use this metric to predict testing efforts, predict defects, predict maintenance cost, predict and identify problematic components, decide on revisions of or components rewrites. So basically how it is being done, let's see this. So we have a mathematical formula, which is V of G, which is equal to E minus N plus 2P, where E is number of edges, N is number of nodes, and P actually is number of unconnected parts of the graph. So let's take this example. So in this example, if you see, we have a flowchart. In this flowchart, if you see, how many edges we have. So total number of edges, the arrows which you can see is 7, and the number of nodes, if you count the number of nodes in this flowchart, it is 6, and therefore we have this value 6 there. And P is 1 because this is one single diagram, this is one single flowchart which is actually performing one task. So if this would have been connected with another flowchart, then we can say we have two unconnected. This P value could be 2, means the number of unconnected parts of the graph would have been 2. But in this case, as we have only one flowchart, so the value of P is 1. And normally you will see the P value is 1 because we do this analysis on one component itself. So then you can calculate the cyclomatic complexity, which is actually E minus P plus 2 multiply E minus N plus 2 multiply by P, which you can get 3. So again, here also, if you're getting a cyclomatic complexity which is very less value, it means the overall complexity of the software is less. If it is very high, it means the complexity of the overall software is going to be high, and if it is low, it is less, I mean. Yeah, and again, this McCabe cyclomatic complexity is additive in nature. Means you can calculate this cyclomatic complexity for one graph, and then you can calculate for 2, and so on, and then you can add and you can get the overall complexity of the whole software. And in order to get a good testability and maintainability, McCabe recommends that no module should have a value greater than 10. So this is also that you can just check whenever you are doing the evaluation, like is it like you are getting some values which is under 10, and it should not be above 10. If it is above 10, then you need to think how you can actually modify the whole code. Similarly, we have one more matrix in software, which is Halstead software science, which actually sees the whole program as a tokens, and means the whole program is being seen as a token, which actually is ultimately a collection of operators and operands. So how we do it? We in the whole program, actually we look for different operators, which we call it as N1, and then we look for different operands, which we call as N2. Then then for all operators we perform summation, which we get capital N1, and then same we do for operands, then we get capital N2, and then we have Halstead formula. Here, for calculating the whole vocabulary that your program has. Like we saw, you can perform n1 plus n2 and so on to get the length. You can of the whole software or the program. You can actually combine this n1 and this n2, and you can get the length. Similarly, you can do for volume, level, difficulty, effort, and faults. So these are different formulas that Halstead actually has proposed, and you can go through these things by your own, and you can just check how actually these things are being used in software development context. So what actually we need to remember from this lecture is like the definition of software metrics and measurement, and why actually we need measurement, and what and different types of measurement, of course, and where actually we can do the measurement on product, process, and people. And we have different ISO models for product, for process, and then we saw like there are different ways actually by which you can perform, you can actually do this calculation. Means you can just check the overall functionality of the software by different methods, metrics. The first was function point. Then you can extend this function point with we saw that this GSC, then Halstead, and then cyclomatic complexity. So these are the four commonly used metrics in software engineering field. But you can also check like if we have some other than these things. Yes, so this was the class for software measurement. So if you have anything to ask, you can just let me know.